Hey everybody, welcome to the next video in our series on rotation. Last time we introduced the quantity of rotation and the standard unit of a radian. Today's lesson will quantify how quickly rotation occurs and how quickly it changes, and set the stage for some comparisons to be made between kinematics and rotation. Let's begin. First off, a new quantity is called angular velocity. And angular velocity is the speed of rotation, or the amount of rotation per unit of time. Essentially, how quickly is something spinning. It is symbolized by the Greek letter omega, which looks kind of like a curvy W. So, the formula then for omega would be the amount of rotation divided by the amount of time. This gives us the formula for the average rotational velocity. Now, you'll hear me say angular velocity or rotational velocity. They're both used quite commonly, so either one is okay. The units for angular velocity are, well, the standard units are radians per second, since the standard unit of rotation is radians. But there are other units possible, degrees per second. Probably the most common in America is to describe things in revolutions per minute, or RPMs. So, just one example, the angular velocity of the Earth as it's rotating around, you know that to be 1 revolution per day, and I thought it might be fun to look up a few other values. So here is a Wikipedia article on a whole bunch of other angular velocities, and I highlighted a couple of them here. This here, the second hand on a clock, it goes around 1 time per minute. Your parents might recognize, or maybe your grandparents might recognize 33 1/3 as the rotation rate of an old record player. Let's see, some more interesting ones down here. Helicopter, as it's going, its blades are going around at about 450 revolutions per minute. By the way, over here, this is radians per second, so that's about 4 radians per second. I'm sorry, 47, because this times 10 to the first. So your washing machine goes about 900 RPMs. Automobiles typically driving around about 960, although here it says that a Formula One race car can top out at about 20,000 RPMs. In your computer, right now, the hard drive is spinning around, and that goes about 7,200 revolutions per minute. A drill, I hate the dentist, drill 800,000 RPMs. So, anyway, just a couple of values to get your heads around how fast things can spin. Now, angular velocity is related to linear velocity by the same sort of formula that angles and distance was related last time. And let me draw a quick little picture for you. If you've got an object that's spinning, we would describe how fast it's rotating with an omega. And then if you're looking at an object or a point around the outside, we would talk about how fast it's moving at any given point. We would describe that with a v, which uses the typical velocity units that we are familiar with. How about some questions? Let's consider how fast we're moving around as the Earth is rotating, or specifically we'll talk about some Ecuadorians who live right on the equator. How fast are they moving? So to do this, even though there is this formula up here of v equals r omega, I honestly will answer these sorts of questions using unit conversion techniques, just like we did before. I'm going to start with the speed that we know. Well, the Earth rotates, its omega is 1 revolution per day. And I'd like to figure out how fast they're moving, what a v is, probably in miles per hour, because that's what we are most familiar with. So I need to convert revolutions into miles, and at some point I'll have to use the radius to do that. And then I'll have to convert days into hours. So multiply by, well, 1 day is equivalent to 24 hours. So now I've got my time unit, miles per hour, and now I've got to get revolutions into miles. And well, we remember that 1 revolution is equivalent to 2 pi radians, which we'll abbreviate with RAD again. And then the radius of the Earth is approximately 4,000 miles. If you didn't know that, that's a fact worth memorizing. The radius of the Earth is approximately 4,000 miles. The circumference of the Earth is roughly 24,000 miles. And since the Earth is broken up into 24 time zones, each time zone is about 1,000 miles wide. So hopefully one of those facts you can remember, and from that you should be able to derive any of the others if you needed. So anyway, if we were to multiply all these out, let's check the units a second. We got revolutions and revolutions, radians and radians, days and days cancel. We're left with miles per hour. And when I divided this out earlier, I got 1,047 miles per hour. So can't really feel that because everything else is going around also, including the entire atmosphere is going around at 1,047 miles per hour. But imagine what it might feel like if all of a sudden you could stick your arm out of the atmosphere somehow, like you stick your hand out the car window sometimes. One more example. Let's talk about how fast our cars are rotating. That is, how fast the tires in our car are rotating. And lots of variables in this particular problem. I'll make up a few things. Let's say perhaps 55 miles per hour. How fast do the tires rotate? And we need a size of our tires. I really have no idea. I'm going to say about 18 inches as a radius. That puts, well, these must be big tires. Oh well. Let's see if we can do the same sort of conversion. Now we have a V, and we're looking for how fast they're rotating, so we're going to be looking for an omega. We could write it in radians per second, but we're most familiar with RPMs probably, so why don't we go ahead and choose that as our final unit. And so I'll tackle this the same way we did before with a unit conversion. Start with 55 miles per hour. And I need to convert miles into, well, the radius is known in inches, so I'll convert it into inches. And that'll take a few steps. Let's see, a mile is equivalent to 5,280 feet. And there is 1 foot, there's 12 inches in every foot. And now we can use the radius. 1 radius is equivalent to 18 inches. Again, I think that's probably a little big for a car tire, but we'll go with it. Maybe it's a monster truck. And remembering that radius and radians are defined to kind of cancel themselves out, we can go now and convert this into revolutions. So it's either 2 pi radians is equivalent to 1 revolution. And let's see, miles is gone, feet. I think the only thing we need to do now is get it into the RPMs. We have revolutions, and I'd like it in per hour, and I'd like it in revolutions per minute. So we'll just tack on 1 hour and 60 minutes. And when I multiply these out, I got 513 RPMs. And typically when I'm going 55 miles per hour, I'll look at the tachometer on the car every once in a while, and it says close to 2,000 RPMs. So there must be some sort of gears. I don't know what they're called, maybe differentials. I mean, it sounds kind of familiar, but I'm probably way off, so those of you who know about cars are laughing at me. But anyway, 513 RPMs. Now, another topic that we can talk about is how quickly an object is changing its rotational speed. That is called acceleration. Angular acceleration is the change in angular velocity per unit of time. Its symbol is the letter alpha, which looks a lot like an A, so I try to make it scripted and a little bit more like a fish than I do my normal A's. And the formula for that is a change in velocity over a change in time. I hope that sounds familiar, because that's exactly how linear accelerations are calculated, except here we're using a rotational speed instead. The units would be, the standard unit would be the standard unit of speed, radians per second, divided by seconds, and so we typically call that radians per second squared. Linear accelerations in meters per second squared. And just like the others, angular acceleration is also related to linear acceleration by a factor of the radius. I probably won't ever use this formula per se, but I might at times use the radius in a conversion problem sort of process to differentiate between linear acceleration and rotational acceleration. So, just a simple example problem. Suppose our car engine is simply idling at 1500 RPMs, and then I hit the gas pedal, and about a half second later I notice that the car's engine is now rotating at 2100 RPMs. My question is, what is the angular acceleration that the engine experienced? So, to do that, the formula is a change in rotational velocity divided by an amount of time. And so the initial rotational velocity was 1500. The final was 2100, and change is always defined as final minus initial. So we'll write 2100 minus 1500 and divide that by a half second, which is 0.5, and that calculates out to 1200. And the units for that up here, these were in RPMs, and the unit down here was in seconds, so this would be 1200 RPMs per second. Now that is a pretty ugly unit with minutes and seconds all mixed together. It reminds me a lot of the linear acceleration problems that we sometimes experienced, where we found a car accelerated from 0 to 60 miles per hour in so many seconds. So let's take a second and convert this into a standard unit. The standard unit would be in radians per second squared. So to do that, notice how I'm going to split up the RPM unit. RPMs means revolutions per minute. And there was already a second in the denominator, so I'm going to also write that down here. And now we need to convert the revolutions into radians, and one of these, the minutes, into seconds, and then we'll have radians per second squared. So maybe I'll start with the time unit, 1 minute and 60 seconds. Now I've got seconds and seconds, so seconds squared. And then I need to go from revolutions into radians. So we'll write revolution down here and 2 pi radians. And 1200 times 2 pi divided by 60 corresponds to about 126 radians per second squared. So, thanks for watching. Be sure to come back soon to see how we can recall our knowledge about linear kinematics to help us solve problems regarding rotation. See ya.